So 15.4, Green's theorem. And Green's theorem is one of the kind of the big important results of the entire chapter. So our first one, a really important result, was conservative fields and independence of path. So what we talked about last time, that was one important result. Green's theorem is our second kind of big result. And what we're going to do, what Green's theorem does, is relate a line integral around a closed curve to the double integral over the region enclosed by the curve. And this makes evaluating line integrals or evaluating double integrals, it simplifies the work a lot depending on the conditions. Green's theorem is named for a guy named George Green, who was a self-taught mathematician. He learned from library books while he was working in his father's bakery. So it's, that in itself is pretty impressive. And he was one of the first people to try to come up with a mathematical theory for electromagnetism. And he was very influential to other people who were working on electromagnetism at the time, including Maxwell, who was the big name in electromagnetism. So the first thing we need to do is define some of the terms that we're going to talk about. So Green's theorem has to do with a simply connected region. So we need to know what a simply connected region is. So the first thing we're going to talk about is a simple curve. So a simple curve doesn't intersect itself between its endpoints. So a curve like this would be simple if we're traveling along the curve this way. And something like this would be not simple. So we're going to use a simple curve to come up with the idea of a simply connected region, or a simple connected region. A simple closed curve intersects itself only at its endpoints. So that would be a simple closed curve, or simply closed. Kind of use those interchangeably. And then something like that would not be simply closed. All right, and then a simply connected or simple connected region is a region whose boundary is exactly one simple closed curve. And that's the kind of region that we're going to be interested in for Green's theorem. So a region like this. Inside this curve, if this is R, this is a simply connected. And one example of something that would not be simply connected would be something like this. So we're interested in simply connected regions. And what we're going to do is, for a simply connected region or a simple connected region, we're going to define the positive orientation as counterclockwise. So when we traverse the boundary of a simply connected region, the region remains on the left as we go around the curve. So, and again, we're defining this orientation because when we parameterize our curve, we introduce an orientation. We want to agree on what our positive orientation is. All right, now we're ready to state Green's theorem. And Green's theorem is, it's really, in chapter 15, is one of the really, really cool ideas, one of the really cool results that we come up with. So we have C is a piecewise smooth simple closed curve. That bounds a region, some region R. And we're in the plane for Green's theorem. And we have these functions m of xy and n of xy, which should be, m and n should be familiar by now. And these are continuous and have continuous first partials. So we're working with nice functions. And they have first partials, just as long as they have first partials in our region. They could be not nice outside our region. We're not really worried about that. So they're continuous with continuous first partials in our region. Then, and here's Green's theorem, the integral, line integral, around this simple closed curve, and the circle just means we're going around a closed path, and we put the arrow in. You won't always have the arrow. The arrow is telling us the orientation around the curve. So the arrow is pointing counterclockwise, so we're traveling in the positive, with positive orientation around the curve. That's what the little arrow on the circle tells us. The circle tells us we have a closed path, and the arrow tells us our orientation. This equals the double integral over R of dn dx, partial of n with respect to x, minus dm dy dA. So Green's theorem is telling us that the line integral around this simple closed curve is equal to the double integral, the line integral of this quantity is equal to the double integral over the region of this quantity. Now when we start using this, this is going to be an extremely powerful tool. It can simplify evaluating line integrals, and it can also simplify evaluating double integrals if we can manipulate the double integrals the right way. And again, remember that this line integral m dx plus n dy, that's the same as saying, this is just the differential form for our line integral. We could write this as the line integral around C of f dot dr, where f is mi plus nj. Those are equivalent. We just have this line integral, and it equals this double integral of this quantity. Now, first, I want to relate this now to what we talked about on Monday. This quantity, what happens if our field is conservative? It equals 0. This is our test for conservative fields in the plane. If our field is conservative, these two things are equal, and this is all 0. So if we have a conservative field, we know that our integral evaluates to 0. And we also know that if we have a conservative field, the line integral around a closed path is 0. So if we have a conservative field and we have this quantity in a double integral, we know we have that our integral evaluates to 0. So let's take a look at the proof of Green's theorem is a little long, a little tedious, and we have to take into account several conditions, several cases. So we're not going to go through the proof. We're just going to accept that it's true. But let's take a look at how we're going to use Green's theorem, how Green's theorem will make our lives easier in a lot of cases. So we want to use Green's theorem here. So we're evaluating the line integral around this closed path. Of y minus x dx plus 2x minus y dy, where c is the boundary of the region inside y equals square root of 25 minus x squared, and outside y equals the square root of 25 minus, or not, sorry, 9 minus x squared. So this is our line integral, and here's our region. So let's make a sketch of this region. So y equals 25 minus x squared. What is that? What is that curve? Circle radius 5, and we're assuming the positive square root. So it's the top half of a circle radius 5. So we have something like this. And the second one is top half of a circle, radius 3. So there's our inner boundary. So our line integral is taking us in the positive orientation around this curve. Now let's think what is required to evaluate this line integral. First off, we have a piecewise smooth curve here. So how many line integrals would we have to evaluate? We'd have to evaluate 4. We'd have to evaluate one along here, one along here, one along here, and one along here. So we'd have to figure out all those boundaries with this 25 minus x squared and 9 minus x squared. And we're going to parameterize those curves, and we have this y minus x, 2x minus y. We have a set of complicated line integrals. But we have line integral around a closed curve, so let's use Green's theorem. So for Green's theorem, what is m? What is m in our line integral? M is y minus x. So dm dy is what? 1. And n is 2x minus y. dn dx is just 2. So Green's theorem tells us all that we need to evaluate is the integral over our region of 2 minus 1 dA, which is just the integral over the region of dA. Double integral over our region. What's a double integral over our region of dA? That's just the area of the region. So what's the area of this region? Big circle minus the little circle, right? And half of that. So the integral of the area of that region is going to be 8 pi. We could evaluate this double integral using polar coordinates because we have these circles. But one of our favorite tools is use geometry. This is just the area of the region. So we changed evaluating these 4 messy line integrals on these 4 different lines into the process of finding the area between 2 circles. That's pretty awesome. So that's how Green's theorem can help us. We have this simple closed curve. We're evaluating the line integral around that curve. Turns into finding the area between those 2 circles. Yes?
What is the y integral again?
Let's see. In this case, if we're thinking of this as a vector field, it would be, we could think of it as the work done moving a particle around that curve. So really, it's we're summing the tangential component of the field around the curve. Questions on that example? All right, let's look at another one. So the clue that you're going to want to try to use Green's theorem is first that we have a line integral around a closed curve. So we have a line integral around C of y squared dx plus xy dy. The other clue is that with the problems that they'll give you is they give you the line integrals in differential form. That's kind of a hint that you might want to use Green's theorem. Yeah.
So when you're given, should we not test to conservative, or should we still try to be conservative?
Yeah, if you see, well, and so
Look at it.
when we use Green's theorem, if dm dy and dn dx are equal, we'll see right away that either way we'll be able to see that integral is going to evaluate to 0. So because we have to take those partial derivatives anyway to test if the field is conservative. So if we're using Green's theorem or we're testing if it's conservative, really we're doing the same thing. Okay? So we want to evaluate this line integral, and now our path is the boundary. Boundary of the region between y equals 0, y equals square root of x, and x equals 9. So it's often helpful to make a sketch of your region. So this is x equals 9. That's y equals the square root of x. So here's our region and our boundary. We're going to go counterclockwise around that curve. Piecewise smooth curve. So again, our line integral involves three different curves, three different paths that we'd have to parameterize each separately and evaluate our line integral and take the sum. But we have a simple closed curve. We have the line integral around the simple closed curve. So we're going to use Green's theorem. So m equals y squared. dm dy is 2y. N is xy, and partial of n with respect to x is y. So we want to evaluate the double integral over our region of y minus 2y, or minus y dA. So for our region, I'm going to integrate, and I'm going to use the order dy dx. So x is going to vary from 0 to 9. Y is going to vary from 0 to the square root of x. And we have minus y dy dx. Nice, easy integral to evaluate. When we evaluate this, this comes out to be minus 81 fourths. This much easier in my opinion to evaluate than the 3 line integrals that we would need to evaluate the line integral. And then the other nice thing about Green's theorem is it makes a connection between our first connection really between our vector fields and our line integrals and what we did in chapter 14 with the multiple integrals. And what we're going to do is we're going to extend this into 3 dimensions, and we will relate a line integral around the boundary of a solid region to an integral over the surface of the region is one thing that we're going to do, or a triple integral over the volume to a double integral over the surface. So we're going to relate these quantities. All right, any questions on that example? All right, let's look at one more. And this is the best one, I think. So we have the integral over our closed curve. So there's our line integral. Already this thing looks intimidating. And there's our path. is this circle. Now, think about how difficult this would be to evaluate, as is. We would parameterize our curve. How would we parameterize the circle? What's our choice usually? Cosine and sine, so we're going to parameterize it with trig functions, so we're going to be in polar coordinates. X equals r cosine theta. Y equals r sine theta. So expressing our functions in terms of the parameterizations, we're going to have something really, really, really messy. Well, let's look at Green's theorem, or go back to section 3 and take a look at this. Take a look at our vector field, both involving the same process. So m in this case is e to the x cosine 2y. Partial of m with respect to y is going to be what? And n is negative 2. Oh. There we go. Did I write it right that time? Yes. Let's see. Did I write this wrong here? I don't want a 2 here. N is minus e to the x. What did I do here? I think I mixed up my m and my n and my partial derivatives here. Let's see. So m is e to 2x, and then this should be no, this should be a cosine, right?
No. What you want to be considered?
Yes.
Oh, that should be it should be 2 e to the x sine.
No, not.
We want the 2. It was perfect originally.
Oh, right. Yes.
Yeah, sine.
Yeah, I was right. I was right the first time. All right, so n is minus 2 e to the x sine 2y. Why did I doubt myself? Dn, the partial of n with respect to x, is minus 2 e to the x sine 2y. So what does this tell us? This is conservative. And so our integral evaluates to 0. So this is a conservative field. The line integral around our closed path is 0. If we would have forgotten that for some reason, and we said, oh, maybe we could use Green's theorem, we would do dn dx minus dm dy, and we would end up with a double integral of 0, and we would see that the integral evaluates to 0. All right, sorry for the confusion. I don't know why I had it right originally, and then I thought it was wrong. So this is one illustration of how powerful Green's theorem is, and how powerful the idea of conservative fields, line integrals of conservative fields, how that can simplify our work. So questions on that last example? And I honestly would really hate to try to evaluate that line integral as is. I'm just, every time I think about it, it's like, oh, that seems horrible. All right. Homework.
You need to change it out of differential form.
When you were explaining that, when you were putting R sine and theta, would you just left it, or you just changed it to polar?
Change it to polar to evaluate, because our boundary is a circle.
Couldn't you just take it out of differential form?
Well, when we do f dot r prime, that really is, that's what this is. Because r prime is dx dt I plus dy dt j. Right, you just have one parameter. And to evaluate this directly, we would change everything, change this form into everything into one parameter. All right, our homework. All right, there you go.